Good afternoon, everybody. Thank you for being with us. Today I'm actually very happy to host and to introduce Cian and welcome back to Venice. Cian Wing. He's been collaborating with us for many years. He was visiting us about 5 years ago. So Cian is a professor at the Department of Earth and Environment. And you probably wonder, professor of what? It's a bit difficult to describe because he does a lot of things. He has many expertise. And he's a professor, I would say, in environmental policy, data analysis. These are the things that he does, mostly for climate change impact analysis and adaptation. He's a modeler. So he's a professor, but he's also a very active researcher. And he works a lot in the field of climate change impact, adaptation, using different methods, modeling, empirical, many different approaches. So today he's going to talk about the new frontier in climate impact and adaptation research. Cian is going to be with us for a week. So today is really the first talk, but then you're really welcome to get in touch with me, with Cian, and come and meet him if you want to further discuss the things that he's going to talk about today. So thank you, Cian, and I think we have time. So let's say about 1 hour.
Yep, I'll be well done by now, and I'm happy to make it more interactive. Okay, thank you everyone for coming. Those in person, thank you everyone for joining. Those online, it's great to be here in Venice once again. The pandemic is at least allowing us to resume some of our connections that we had built before, and I'm very grateful for the opportunity to come. Thank you to Enrica, thank you to the staff at CMCC for all of their help in getting me here and getting me to give this talk. So the title of the talk is kind of clickbaity. It's called Cloud Computing, Revolutionizing Climate Change Impacts and Adaptation Research. And I don't think on the list there was the question mark at the end. I put the question mark because I'm almost certain with talks like this that there's at least one person in the audience who is going to be, what are you talking about? I've been doing this for years. So to those of you who are familiar with all of this, you can have a coffee, just put me on mute. But hopefully I'll be useful to some people, and I'll try to speed things up a little bit so that I'll end with a bit of a demo, and I can show people some of how this works. Also, this is a personal talk that's kind of based on my own knowledge that I've accumulated over really the last 1.5 years, trying to invest in understanding how these systems work and how to develop new workflows to increase the speed with which we can bring ideas to publication in the impacts and adaptation space. And so just starting with something very whimsical. This is something I used to read to my kid, Tommy de Paola. This talk is all going to be about the cloud and the use of cloud-based services, and I find it very interesting because it's kind of the Wild West right now. Even though much of the technology that we're talking about today, that I will talk about today, is kind of old. It's kind of mature technology that's being used in different ways. The ways in which it's being used now are fun and interesting, but also somewhat nerve-wracking and also somewhat daunting for people who have not done this before. And so I feel that my niche in this talk is to try and go some ways towards helping people navigate the fixed cost aspect of this. If I want to do X, what are things A, B, and C that I can do in order to get up to X. So let's go and see how far we can get. Okay. So I have come to believe, and I think others in the scientific community share my opinion, that the cloud is really the way of the future. Thinking back to the good, bad old days of CMIP 5 and the papers that I published with Enrica and Malcolm, and even papers that I have in process now, we spend a lot of time worrying about downloading data. And so the old model was to use institutional high-performance computing systems that we would buy into, BU is a buy-in system. So I have to pay money to buy for disk, I have to buy a node in a giant cluster. And I'd spend money that I'd raised on a grant to buy big computing clusters with lots of storage and lots of compute power. And then I'd wait. I would spend a lot of time, electricity, CO2 emissions, downloading and storing a lot of data that would be on nearline storage on disk, and then processing that set of stored data for different applications that I wanted, which would be different papers. So there's this huge fixed cost. And the metaphor that I have is this image here, where you have public-private partnerships or governmental entities like NASA or Copernicus, who have essentially a data lake, a very, very large institutional store of data. And we go as researchers and write grants and spend money to build our own small data lakes as high-performance computing environments. And then we use tools like FTP, Globus, wget, to basically drain parts of the big lake into our small lake. But what's the metaphor here? Both lakes are storing. We're just creating copies of the data, and that's kind of wasteful. It's wasteful in money, it's wasteful in time, it's wasteful in energy, it's wasteful in CO2 emissions. And so can we do something different? Well, the cloud has sort of revolutionized the way to connect to individual users, because now the new model is that you try to park at the lake. Data exists in centralized repositories, and those repositories themselves are maintained by major cloud providers, Google, Microsoft, Amazon, and that is the metaphor of the lake. But now we can log into these providers directly and use cloud compute services, processors that are physically proximate to the data that we are analyzing. And that is the key reason to do this, because what we obviate for researchers who always want to be first to publication, we obviate the time and effort spent in copying data, okay? So what that looks like using, and apologies for the very American analogy, you all don't have these in Europe, but these are called RVs, or recreational vehicles. They're basically a house on wheels with a toilet and a kitchen. I see horrified looks from the audience, but any Americans who are joining, they would understand this. Probably even been in one. I don't, sorry. But the parking at the lake metaphor is that the lake is the cloud service provider and their cloud assets, their cloud hosted data sets. And a login, how you park, is cloud compute instances, meaning you create a virtual machine on one of these cloud data storage entities spun up as you want it. And that's the key. You don't have to have a machine running using electricity, having disk on nearline storage at the same time as some other provider is doing that. That is what gets rid of the waste. You use it in time and in space where you want. So you have less time, money, worry, electricity, CO2 emissions, spent moving the data, assembling the data. And it turns out that because of the tools and technologies that we have the capability to move seamlessly through many, I put all, that's kind of clickbaity, but many of the steps of data assembly, analysis, and visualization in one single environment. And you don't have to move the data back and forth. So that's the mantra of this talk. Don't move the data. Find ways to move the instructions. The problem is that oftentimes when you have to move the instructions, you have to move them in different programming languages, because there are bottlenecks in this process. Even though you only download what you need in terms of results to individual users, to fully exploit this potential, you need an analytical paradigm shift. And you need to sort of figure out the ecosystem of who has the data, how do they allow you to access it, how do you want to access it for what you want to do. These are kind of mini fixed costs over and over, rather than the big fixed cost of buying a server and downloading all of the data so you can. Why do this? Well, the cloud and cloud-based services which are basically monetizing the way in which large companies have run the World Wide Web for the last 15 years. So the technologies that have done this are well worked out. They've been used to serve us web pages on our phones, on other devices for years and years and years. And what cloud providers have figured out is like, oh, we can sell these services as a service, software as a service, disk as a service, compute as a service. And there are companies that are willing to pay for it. And because companies are willing to pay for it, there's huge cross-subsidization, which is that you and me can use it largely for free or for very cheap. And so increasingly what is happening is that large amounts of data are freely accessible. There's zero cost to sign up for a Google account. You have to watch lots of ads, but that's okay. It enables you to sign up then for things like Google Colab or Google Earth Engine with your Google account. You can sign up for Microsoft Planetary Computer for free. I don't know, and in this talk, I will not talk about Amazon AWS because simply I have not used it. I've used Oracle Cloud and I found it pretty terrible because you have a lot more control over your server. It's not a dedicated environment. The key, however, is that government agencies are increasingly relying on cloud providers to host environmental and social data sets. And so remember, I talked in the last slide about providers like NASA or providers like Copernicus. Well, where do we think that data that we download from ECMWF, you want the RFF land to do some historical analysis to link with some social process in a regression, where do you think the data lives? Those data live in the cloud. The very services that we would use here are the same services that are being bought by these entities. And these entities have got out of the facilities hosting game. ECMWF does not control and own and run their own servers. They fired all of those people, and those people are now working for Amazon. And Amazon is selling them that service as a service. And so why download from outside the cloud, which is really the cloud, when you could just go into the cloud and use the data in a physically proximate fashion without moving the data, okay? The other thing is that the computing power of these mega corporations is just breathtakingly vast. Cloud providers' free tier resources often exceed the capabilities that an individual user could hope to mount on their own for free or even for modest means without going and writing a dedicated grant. And there's potentially vast capability to store results, principally because it turns out that in addition to Copernicus or NASA or other places buying compute services and buying cloud services and using them, our own universities, our own university institutional affiliations, they buy cloud services for their payroll, for their human resources. And as a bundle with those, they negotiate agreements where they have access to AWS, to Microsoft Azure Blob Storage, to Google Drive. I have an institutional Google Drive subscription that provides me nearly unlimited. I was warned by my IT, don't take the word unlimited too literally, but near unlimited storage for processed data. So if you don't have to store the native data set and can keep it in situ, and you have the ability to store the processed data, all you need to do is move the instructions. And so the rest of the talk is to figure out, well, how do you move the instructions and how do you think about that? The catch is that there are bottlenecks and limitations that are specific to each cloud provider system, and navigating that is a pain in the ass. I'm sorry, but I'll just be straight with people. It is a pain. But that's kind of why I'm giving the talk, to try to help people figure out their way through this, with the caveat that this is just one person's experience. I'm an old man, I'm in my 50s now. So you young whippersnappers who are smarter than I am may well figure out ways of handling this that are better than what I've done. Take what I'm doing here not as gospel, but as a start. Go forth and do. Okay. First of all, architecturally, what is the cloud? Cloud is basically three pieces. The first and most important, and why we're here, is that it is a vast array of distributed data storage in data servers located around the world connected by very, very fast bespoke networks, right? This is the infrastructure that Microsoft, that Google, that Amazon has built for themselves internally. Okay. The key to accessing this data storage is sets of parallel job schedulers, which means that the notion of a data set as a set of files no longer exists. The blocks of the individual files on disk may be physically on disk in different data centers in different time zones, and it doesn't matter, right? We view that on our desktop as we have an icon, but that is a metaphor for a system of network data where the network is under none of our control. Okay. However, part of the monetization of cloud services has been to give the people who purchase the services, either compute services, disk, or other things, access to the scheduling capabilities and therefore the parallelism that underlie that storage. So now if we write a loop and we do something within the loop to process data, that loop runs faster because behind the loop is simultaneous asynchronous execution of everything in the loop and a system to keep track of what was executing where in the world and when, and then a system to bring all of that information back together and give us the results of the loop as a metaphor of one file. That's the speed up. Sure, that's asked.
In the loop, you would have a task being performed across the different data centers or.
Yep. The task is different data centers and different cloud providers will give you different means of different degrees of control as to how much that happens. At the free tier, you don't have much control, but if you pay, you have a lot of control. This is the other part of it. I am of the non-paying variety. I'm old and I'm cheap. So everything I do will try to exploit the speed up at the free tier. But as we will see, if you pay, you get more. But given that it's the Wild West, and given that in most parts of the world, if people want to rob you, they will point a gun at you. But in the United States, they say, sign here, please. Okay? Caveat emptor. Be careful what you sign up for. And I will get into that with an example in a minute. The third piece of the cloud for our purposes is cloud service subscriptions, which are compute instances. Accounts on Microsoft Planetary Computer, Google Cloud, or Colab Pro, AWS, Google Earth Engine, which provide you with a compute engine and persistent disk that is accessible via a web browser. Compute engine will have different amounts of RAM, different amounts of native disk that you can use for Scratch, different kernels that provide functionality for different languages, R, Python, JavaScript, and different libraries that provide the tool chain that you can really use to exploit, to process the data. Dask, which helps you control parallel job scheduling. TensorFlow, which helps you run ML models. I don't run ML models. I like a regression because I like to see the coefficients of what I'm doing. And principally what I'll talk about at the end of this talk, which is XRA, which is native geospatially aware processing of space by time by band data cubes. Okay. The red box really differs depending on which cloud provider we're talking about. Generically, they're very similar, but they differ in their details, and they differ in the blue arrows in terms of how you can access the various services. You can also, from your cloud service subscription, export your finished data once you finish processing it to either cloud-based storage. You buy Amazon Web Services S3 buckets, or Azure Blob Storage, or Google Cloud Storage to a cloud project, or you can just download them to external storage, since that is what I do, since I have a high-performance computing system of my own, and process the results there. All of how big that arrow is and how twisty twirly depends on how comfortable you are and how much access there is for doing the things that you want to do in the cloud itself, and just downloading essentially the image that's going to go into the journal article. And then you put on GitHub all of the code in Python. It's like log in at the free tier and run this code and you'll get the results of the paper. It is possible to do that and just hand, PNAS, here's the Jupyter Python notebook. And if you don't touch the data, there's nothing physical that it is possible to do that. There are papers right now that are already doing this. Okay, this is kind of the way of the future. What happens is sometimes, you can't get on your compute engine R, and R has a particular estimator. I'm going to tell my next talk is going to be on a health application, which has millions and millions of individual patients. And so I need a code which can run a very fast fixed effects estimation at extremely high dimension fixed effects. The only package that I know that's able to do that is Laurent Berger's CEST, right? They don't have CEST on a Microsoft Planetary Computer. So I have to download and I'll use on my own high performance system. So architecting this and how far you want to go within the system depends on what you want to do and the limitations of the particular system that you work with in the cloud. But the important thing, and the link to the previous slide is there are external data repositories that can be used with this system, and your model was to collect your external storage to those external repositories. With the movement toward cloud hosting of those external repositories, we just carry our instructions. That's just figure out how to carry your instructions. Now that's going to require certain things, and those things are going to depend on what cloud we're talking about. Sorry about the dense slide. I will provide copies of my slides so people don't have to read while my head is bobbing back and forth. But this is sort of my attempt to systematize the Wild West. We can think of different systems in terms of three characteristics: the assets, the kernels they provide you for programming languages, and the amount of RAM, disk, and storage. These are sort of the three basic ways in which I have learned to think about these various services. So let's go through them. The three systems I'm going to talk about, again, apologies to Amazon heads. Those folks who are already in AWS, you will educate me. I only have so much time. So the three systems I've experimented with are Google Earth Engine, Google Colab, and Microsoft Planetary Computer, and I'll go through each of them. Google Earth Engine is renowned because it has a massive array of remote sensing, environmental, and increasingly social science data sets. And it has very limited to none in terms of options for accessing external repositories. So it's a closed ecosystem, okay? Most of those data sets, not all, but most are historical. So for instance, ECMWF, ERA5, land, hourly weather, or they can be model-based. NASA Next GDP, CMF5, belatedly, almost as soon as CMF6 comes out, they put CMF5 up there. The kernels that are provided, pretty much, there is a way to use Python, but pretty much the way you access this is through native JavaScript environment, but even JavaScript doesn't help you if you're a Java head. All of the action is in their EE API function calls, and there are pages and pages, an entire website dedicated to EE function calls. There's an entire section of Stack Overflow and cross-validated dedicated to how to do these types of things, how to use these function calls in a particularly arcane way that is required to access the way in which these assets are held in Google storage. Okay. It is very good at what it does, but it is very specialized. This is the trade-off. So it affords the ability to undertake large-scale spatiotemporal data processing, very easy geovisualization. I'm an economist, so I don't care about that. And empirical modeling capacity, unless you're modeling something just like a regression, you can't do much with it. So it's basically you process it and you get the data out. Google is a funny company. There is limited compute memory, but job scheduling is seamless, asynchronous, parallel, and very easy. Okay. It's also reliable, If you try to run too many jobs, they'll cut you off and just kill all your jobs. But they don't tell you what that limit is. Google is, especially at the free tier, I will go out on a limb and risk being sued, deliberately opaque about what the limits are. What is it that you're buying? What is it that you're using? And so the hard thing about coding here is you could tee up a very, very big calculation, only have it to run for a few days and fail completely. And you won't know in advance. You won't know how big is big. And so other researchers I have talked to have resorted to making hundreds and hundreds of small files just to make sure that each individual job has a better chance of making it through Google's scheduling system without incurring the wrath of the Reaper, which is the process Reaper, which is the demon that runs in the background and says your job is too big, you're using up too much resources. You're done. You're dead to me. Tony Soprano. Okay. Tightly integrated with Google Drive. If you have an institutional subscription, storage is essentially unlimited. So it's great. I've used this system. I'm using it right now for a health application. Stuff has taken weeks to run, but it's run successfully. And I've downloaded it to Google Drive, and I can get it out of there with RFlow, or even just click, download. Google Colab. The thing about Google Colab is its potential. I haven't found a way to make it live up to its potential yet. You can, through various means, access a vast array of Google Earth Engine, Google Cloud, and BigQuery, Pangeo, CMIP6 data sets. You have access to external repositories through Google Colab. I pay for Google Colab. I pay $50 a month off of a grant. It's, small potatoes, but it provides me with the functionality I need. Connecting to these different data sets, even within Google, is not at all seamless. It's not at all seamless. It requires you really to program. Things can fail. There are new Python packages being continually developed to address this. Kernels, they give you a lot of kernels. You can run a native Python environment, but in your Python Jupyter notebook, you do %, capital R, and all of a sudden, from then on in the cell, you have R access immediately. Okay, so very, very flexible. So you can write mixed code. One cell Python, one cell R, one cell Python, one cell. Right? Very, very flexible. Workflow parallelization with Dask. So it means things run in parallel, things are fast. When they do run, the infrastructure is fragile. So even with Colab Pro Plus, where I'm paying, Python packages I have found can randomly fail depending on a compute instance. That means the code that I wrote yesterday that is running today, when I log in tomorrow, it may not run. And what I have to do is take down the entire compute instance, log out completely, log back in, spin up a new compute instance. Yes, it's 5 minutes, but it's the irritation of that 5 minutes. Log back in, and all of a sudden, all my packages will work. I just seem to have got a bum node on the rack of the particular data server in South Africa, or Uruguay, or Kazakhstan. The one that I got was not good for what I wanted and wasn't configured properly. It happens. But in working with the system for about 6 months, it happens quite a bit. All right. So again, I'm not paying, well, I am paying now, but caveat emptor. Right? There's also a maddening lack of transparency, as only Google is good for, right? The detail on allowable concurrent sessions or memory allocation or anything like that is completely hidden. As soon as you click the plus on a Pro Plus, put in your credit card, please, right? So you can pay, but even now I'm paying, I don't know what I'm paying for. There's no precision as to what I'm paying for. The contract is, we'll give you what you think you deserve. Right? And if you launch a big job, you can sort of see the problems arising with that. So it's good for small scale, tightly focused stuff, and stuff that you can modularize. Stuff that you can modularize and pick off in bite-sized chunks. There is this English expression, horses for courses. If it's a muddy track, you want a horse that will run in the mud to be able to win the race. If it's a dry and dusty track, you want a horse that's good on hard, dry ground. Horses for courses. It depends on you, the user, and what you want to do. But these are sort of a map of the capabilities of what you can use it for and what it's good. Last one is the one I use most, Microsoft Planetary Computer. Their catalog of assets is really small. Its growth path is unclear, but the big draw is NASA next GDDP CMIP6. In the process of writing this, I forgot to add, they don't have the RE5, but they have the RE. So if you can get away with 0.25 degree, you can use Python to access ERA5 quick. Much easier. I've done a test, much easier than Google Code. I'll tell you why in a little bit. Okay. In terms of kernels, you get native Python, you can get R, you can get QGIS. There's workflow parallelization in the back using Dask, and the infrastructure, it seems, would appear much more robust than Google Colab. It just seems to run better. Your code, there's still some problems at times, and you have to log out and create and spin up a new compute instance, but it happens much less often, I find, in my experience, than even using Google where I feel. Sure. Yeah, also
the Microsoft Planetary Computer seems to be the best in terms of infrastructure and flexibility in terms of languages you can use, but it's essentially NASA next CMCC. So
there are a couple of remote, there's ERA5 now, okay, and there are a couple of remote sensing data sets, but there are only 39 data assets. So I have it on good authority that Microsoft Planetary Computer, the team is like 6 people worldwide. It's really on a shoestring, but it's leveraging this vast infrastructure that Microsoft has, and it's one of the top 5 corporations in the world, right? So again, it's specialized, but also Microsoft seems to be much easier in providing access to external storage. So for instance, for NASA Next GDDP CMIP6, they have ingested SSP245 and SSP585. The first thing, Malcolm sends the link, GDDP CMIP6 is here. Oh, what happened to SSP370? We don't see it because they haven't processed it. But it turns out that I've written code to be able to FTP it across into the cloud, and it seems to work an order of magnitude faster than me downloading it externally. Why? Well, guess where some of these data are, the native data are hosted, right? They're using Microsoft for part of their data holdings, and that's why it's moving so quickly, right? So I'm still using mea culpa, some CO2 and some electrons, but I can move the data faster. And so at least it's easier to publish. The thing about Microsoft Planetary Computer is that their free tier memory and persistent disk are very limited. They're very, very cheap. There's no Google Drive integration. And so what that means, if you try to install, a Google Drive, it will actually prevent you from installing that Python package because it's their competitor. Why should I have an open system where you can use my competitor if I can make you pay? Bottlenecks, right? We are all the victims of capitalism, right? So you can't integrate with Google Drive. The extent of Azure blob storage integration is unclear. Here is the caveat emptor. I went through a cloud broker. A cloud broker is a class of business entities who mediate between these big corporations and institutional buyers. The institutional buyer says, I want X functionality. The seller says, I have these services. The broker uses their experience to understand, how do I match X to Y? As part of that service, you uses it for payroll and HR and big databases for the university. Part of it is extended to the research community at the university. I was able to get access to these cloud broker. After a month, they came back and they said, well, we really cannot guarantee that if you purchase blob storage, you will be able to save your results there and not get charged when you try to take it out. Because all of Microsoft Planetary Computer servers are in Western Europe. And it turns out that if you have a data center in one part of the world and you're trying to download it to your high performance computing system in another part of the world, many cloud services monetize that transfer. And so all of a sudden you sign up for this, you make your data transfer, and all of a sudden you get a huge bill. So I would urge everybody to sign up for, make an account on, and look at the listserv on Pangeo. right? Pangeo.org. And there are people who have wrote in saying, how can I realign or reorganize my cloud workflow so I don't get hit with unexpected access charges in the thousands of dollars, right? So again, be careful what you're paying for. And without the guarantee that I could sign up for the service and just download what I needed, when I needed, as I needed it, I'm not gonna buy it. I'm not gonna pay for it. I'm not gonna pay for something where I'm paying to be part of a closed ecosystem. I'd rather work more slowly at the free tier, right? And so this is again how you organize part of a group. Do you have people with the individual accounts and say, okay, well, person A, you're responsible for this piece. Person B, you're responsible for this other piece. Person C, you're responsible for this other piece, and you all do it in parallel, parallelizing over the humans rather than the machines in the cloud as a way of circumventing these sorts of obstructions to a workflow. This is a question of how you organize. Okay. So let's just do a little dog and pony show and tell. You know, Google Earth Engine. This is where people are probably laughing at me in the background because lots of people have already used this. There's lots of data, swimming in different types of data. So there's weather data. There's data sets on wildfire as a U.S. Department of Energy project we're working with wildfire. There's data sets on air quality. I'm working now with a couple of postdocs at the BU School of Public Health to link air quality from wildfires to health in the United States, since the United States West is burning. There are increasingly data sets with population and with things like night lights that you can access. There's also CMIP5. Hopefully at some point CMIP6 will be available, but let's talk about it because already we have more flexibility working in Python rather than JavaScript. And so essentially the metaphor here is there's two types of geospatial data sets that are the assets. The assets are what I just showed, which are sets of raster images, which are data cubes, latitude, longitude, time, and different bands for a data set. And there are also other assets that can be merged geospatially. And this is the real advantage of Google Earth Engine, large scale merging of raster data with what are vector polygon features. So the metaphor that you work in Google Earth Engine is features and images, right? So you have a feature collection or an image collection, and it's merging the two geospatial. What does it look like? For those of you who haven't used it yet, this is what it looks like when you sign up. There's a native code editor. Well, I can go through actually. There's a separate free sign up using your Google account. There's a place where you have a code repository and it can be backed by GitHub. This is where the magic takes place. It's a native JavaScript environment. You have cloud optimized EE geospatial API functions. There's strict separation between client-side visualization and server-side data retrieval processing using cloud-based assets. This is, for me, as a person who's just, I learned in Fortran. Okay, you sit down and you program the thing, you write a loop, you need to write a loop, you write a loop. No mass. No loops. You have to use map, which are functions over image collections, time slices, or over spatial features, and that facilitates seamless asynchronous parallel execution of geospatial processing. Map is a loop, but a loop on a server side that hands it off to Google schedulers that allows you to have the loop iterations happen in parallel, distributed over space. If you write loop here, you're using all of the power that is responsible for just this compute instance that's giving you this web page, right? You cut yourself off at the knees, as they say, and you're walking around like this high because you're only using this compute instance. You're not using the entire cloud. Visualization of collections and calculation of results using Google Maps. This is very, very useful with debugging. If you do a geospatial process You do it on 1 or 2 slices, and then you show what the slices look like. It's very easy to do that. You can inspect the attributes of whatever you're querying on a map in terms of polygons or pixels. You can also check your program execution. You can do some display of output, though small scale. If you try to output a big output, it will just, the whole thing will just fail, it will crash. And you can do some debugging, though I have found debugging in this environment extremely tedious as to what is going wrong. The magic is that if you run a code like this, which is a New York City application looking, we have the universe of bills for New York City housing project. So we know every monthly bill for every New York City housing project going back to 2010. And we want to understand the dimensions of energy poverty because this is where poor people live in subsidized apartments in New York. We have their bills. And we don't have the individuals' bills because those are masked, but we have the metered data every month. And so we have thousands of properties across the city of New York, different meters on those properties, big housing projects. What we do is we query the points of where those parcels are, and we get from AR5 land all of the data for those parcels for every hour of the month over all parcels. And then what we do is we chunk it out into months and run each month as a separate job. Takes weeks to run, and I have to do it in batches because I don't want to set up 100 of these and have them all fail after 10 days. I set up, 7 or 8 at a time, log in on a Sunday morning. If it's still running, log back out and get breakfast. If not, I batch up another 8. And so just developing a rhythm within the limits of the software environment, right? But it's very, very reliable. If you go slow and steady, you get the data in no time, and it's faster than FTP and more reliable. And you have the processed data without having to download the whole thing and then do what is the R raster package extract, right? That's the key. You don't have more data than you need, and then you have to like blow your computer's memory trying to do an extract for only the parts that you want. You've done the merge in the environment using the cloud as it kind of was meant to be. The code can write output directly to Google Drive. So these files being saved here are being saved to my institutional Google Drive directly. You can save tabular data as CSV, vector data as shape files or KMLs, and raster data as GeoTIFFs. Very, very flexible in terms of output. Yes?
For example, here I see temperature.
Mm-hmm.
So would you, let's say, suggest to download the raw temperature and do any calculations such as CDDs or beans locally, or would you do the calculation directly here?
I would, given that these are hourly data, I would really try my best. If this is going to take time to run, it's not going to take that much more time once there's the feature collection to aggregate the hours to daily averages, compute the CDDs, and then you're dealing with very, very small files at the end. I mean, I would say in my heart that the best way to do it would be in the cloud, but with my head, practicality says how you do it is you have a horse race. You do it with the extra code to do your CDDs and HDDs here. You do it just figuring out the temperature data and downloading it and doing the other thing in R on your HPC system. And you do the same head-to-head comparison. And whoever wins that horse race, that's what you do. That's the way to be efficient. No, I'm serious. That is the way to be efficient. I am totally not doctrinaire, right? Because the ultimate objective is PNAS, right? That's what you want, right? All of this is in the service of that objective. Do what works. That's the mantra. Just do what works. Figure out what works and do what works. The problem is, as Enrica asked, it's the figuring out, right? It is, we are not conditioned to do those kind of tests. If somebody had told me this 2 years ago, I would say, what are you talking about? I'm not a software developer. But in some ways we are, because what we're trying to do is to figure out the most efficient thing given the bottlenecks of the systems that we're working with. And given that so much of this is not under the user's control anymore, you're no longer in a high-performance computing environment, right? It's like if you're using a cluster and there's not a package and you have to get somebody else to install a package for you. It's that kind of thing, right? So we all face workarounds. This is just the other way of doing it. So my assessment is that the best use of this is on the inbound side of empirical analysis, because most of these data sets are historical, right? So if I'm running some social system where I have a criterion, an outcome that I care about for a climate impact, and I have a vector of environmental variables X, that's my vector of environmental variables. How do I set it up to get those environmental variables? That's what I want. Okay. The key thing is you know, an econ graduate student, they will go and they will sit in the ministry in Delhi and get their data set that they're going to write their papers on and come back and they have their CD-ROM encrypted with the data from, you know, the Indian Statistical Office or something like that. And now they have to match environmental correlates of whatever they're studying in environmental economics to do that. This is the system that allows efficient processing of environmental data at the spatial and temporal resolution of the human systems that we are studying. And if we think a little bit about that resolution, we can match in time and space. MPC. MPC is pretty new, only about a year and a half, maybe 2 years old. Pretty robust. Let me show you what it looks like. This is their version of the little schematic of what is the cloud. You have a web browser that connects you, enables a middle schooler with a little Chromebook to basically process the entire CMCC archive, which I just think is fantastic democratization of computer science. You access the cloud through Jupyter Python notebook in a web browser. That gives you access to 2 key technologies for the different storage assets that Microsoft has. It allows you to asynchronously and in parallel query those using Dask, and it allows you to ingest the results into this system called Xarray, which then allows you to very easily subset, slice, dice, and process geospatial, even temporally varying data. In terms of your environment, you have a nice smorgasbord you can choose from for what you want to do. I typically just use Python. And that's what the Python environment looks like. Okay, this is what you get when you start. Some things about the environment, there's very limited compute memory. One thing I respect Microsoft for is they're cheap, but at least they're honest about the fact that they're cheap. You know, Bill Gates, yeah, I did it, right? They only give you 32 gigabytes of memory. And so what that means is now you have to think about computer programming, right? Now you have to think of not being wasteful, creating big loops where you're ingesting a huge amount of data because you basically blow up your memory allocation. Right, so you have to think. You have to think about keeping within that limit operationally. The next thing is that you have a very chintzy persistent storage. Your persistent disk is only 25 gigabytes, about the same size as a 3-tier Google Drive. It can be increased by purchasing Azure Blob Storage, but the cost and the terms of access between that storage and your HPC system, not really clear. This will probably change, but beware data egress charges. So what's going on here is that, you know, these data egress charges are the cost of doing business for large corporations who are mining, for instance, our tweets or our social media posts, or even now, unfortunately, the cookies set by, you know, Reddit on my phone when I look at a particular post and what I'm looking at to target advertising to me. This is a multi-billion-dollar business. And so in a multi-billion-dollar business, if it's Cian with a few $1,000s from a National Science Foundation grant, I'm a rounding error, right? I'm like 6 significant digits out. They don't care about me. But we think that over time, these charges will become more transparent, and that is one thing that may change, especially as institutional subscribers who are universities say, listen, we would like you as part of our bundle that we negotiate to extend these services to researchers, but in order to do that, you have to be clear about what the researchers are getting. So demand from us to our institutions and demand from our institutions to these big corporations are what's going to make the change. The change is ultimately us. If we lobby, ultimately enough people in the world will come together and make these people realize, hey, you have to be clear about what it is you're charging. If this is part of the enterprise, it can't be surprises, right? If people are rounding error, then you can't have surprises in the thousands of dollars. There's a limited catalog of geospatial assets. So I just went through three things: limited, limited, limited. It's like, well, why are you telling us to use this again? Hello. Well, the big draw is that they are the one set of people who really have access to NASA and XGDDP CMIP6, so others may have that. I mean, I use back channel connections that I have to talk to people in Google, and they said, sure, we're on it, we'll do it. That was 6 months ago. Crickets, radio silence, right? They have SSP 5851425. All the other SSPs can be downloaded from NASA Ames Threads endpoint. I wrote code to do that. Giacomo has an example of the code. I'm happy to share with other people, diffuse that technology. They also have the RFF-CMCC. I just haven't been able to use it and connect yet. But boy, if I have to spend weeks dealing with RFF-CMCC land, and I don't need hourly, right? And I don't need 0.1 degree, but I could use RFF-CMCC at 0.25 degree. Not too bad, right? So my next task is to see if I can connect through Python and just access it very quickly. Because part of the draw is to be able to access stuff quickly. And for a paper that we're writing with Francesco, I was able to process, what is it, all the CBDs in 2 days? All the CBDs for 32 CMIP6 models, 2 SSPs and historical, 2 days. Yeah, granted, I was like, click, 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 checking to see if it would run, right? Because it failed a couple of times, but 2 days. Right? That's what it means to be first to publication. That's what it means to be first to publication. That's the difference, and that's why I'm here, because I love you all. Right? I'm giving this technology to you first, not to Max Alham. He's probably on the call taking them. And again, you can connect these assets to X-array data processing that leverages DAS backend parallelization. So even one reason to use X-array is that X-array leverages DAS on the backend seamlessly. So you have a huge data cube. It's chunked the data cube across different servers in the world, but it doesn't tell you. All it asks you, do you really want me to chunk this? And it does its magic. So let's talk about Google Colab Pro. The promise of this system is really the ability to use Python to connect to Google Earth Engine or BigQuery, Google BigQuery datasets. I've been working a lot with a new package that came out, I guess, late last year called WXEE. It's translation of GE assets to X-array datasets. The problem with it, as shown by this example, is that first of all, connecting to GEE still requires API function calls, except now not in JavaScript, but now in Python. So you have to set up your dict call in a different way. It's a pain in the neck if you just got accustomed to JavaScript like me. But the biggest downside of this is Google is so vast already that the data still has to be copied, albeit within the same Google ecosystem. It's one part of Google copying the data to another part of Google, and that takes time. It can take, for my New York City application, I ran a test, and to run that for hourly data, just running a year can take a day, right? And that's just copying, and sometimes if I copy too much data, it will fail. And so what's happening is that you're running up against the server-side limits that are not clearly communicated and that are opaque on the end of Google Earth Engine, even though you have this nice Python environment. So it's like having a Porsche 911 on the road in Trinidad, right? You hit the gas and all of a sudden you're off the end of the island. You're all dressed up with no place to go. So I'm working with the system to try to figure out, you know, what is it really good for? What is the real advantage here? And it's worth some more experimentation. I think there's potential. I just have not myself found a way to crack it with my limited computer science knowledge. What's the big draw? The big draw is here really Pangeo Google Cloud, which provides the entire 36 petabytes of CMIP6, but raw, untransformed, no downscaling, no bias correction. But if you ever want to work with native climate model data, this. And it's in the part of Google where accessing this stuff from Google Colab, quick, very quick. Almost as quick as Microsoft Planetary Computer. So it's good for impact assessments with raw GCM projections, and I'm on this DOE grant, the paper by David Lafferty on communications with an environment. They actually compared NASA Next GDP5 with the raw GCM data, and they found, well, the bias correction and downscaling really does change the moments of the data. It compresses, for some model, it radically compresses the tail. And given our impact functions where all the impacts, the very large marginal effect of the impact is in the tail, that's worrying because they use Wolfram Schlenker's hockey stick for corn yields. And they found that that inward movement of the tail from the native model to the downscale model dramatically reduced the apparent impact on corn yields. So the criticism from Wolfram, who I'm on a USDA grant with now, is like, hey, you know, Ian, your paper with Enrica and Malcolm in GEM, you probably want to try and use native climate model data with the same transfer function because you're probably not getting the tails right. So, I mean, this is science. So the computation starts telling you, starts opening avenues, right? Before our symphony ramps up, let me just close. So we've had a dramatic increase in the size of environmental data sets and a trend towards storing them as cloud-based distributed data assets, and that has the potential to revolutionize climate change impact research. What we see is when we can get it to work, a dramatic speed up from processing weather and climate in situ into forms needed for analysis rather than really wasting, I think, resources as we have been accustomed to doing because there was no other way and we didn't know any better. There was no alternative to copy those assets on our own and then manipulate them on our own. The scientific community has already developed and is continuing to refine many technologies to support these workflows. DAS, XRA, XCLIM, which is built on XRA, where you can do all sorts of your own downscaling. You can do, for instance, for this fire project, I'm computing fire weather indices using NASA Next CMIP6, right? It provides you the functionality that you can compute all kinds of indices. And these technologies are there. They're Python packages, they're downloadable. They're extensively, though badly, as only computer scientists can, documented. But people have used them, and you can look on GitHub, you can look on cross-validated, you can see examples of how these things are used. But taking advantage of these opportunities is going to require investment. You got to shift your headspace to working in the cloud. And I would think that, you know, this is the biggest thing. It's a question of whether you really want to. Whether you really want to undertake that mental shift. There's some people who won't, and that's okay too. But me, I have drunk the Kool-Aid of don't copy the data. Move the processing instructions to the data, and the particular instantiation and how you do it is going to depend on the problem at hand. We're also going to need to invest in learning new technologies, JavaScript, EIEE APIs for the JavaScript, Python, Dask, XRA, XCLIM. One of Wolfram's students, very bright guy, he was like, please tell me you can find a way to use Python to query Google Earth Engine. I was like, yes, you can, but you have to do things in bite-sized chunks. You have to do it from Google Colab. Just learn. The time it would take you to do what you want to do, just learn JavaScript. just learn JavaScript and do it in a native environment. It's a pain, but it's an investment. It's an investment in moving yourself forward. And then the hardest part, which I've tried to dispel here with this talk, is to try to navigate the peculiarities of different cloud provider systems and the mechanisms by which they give you access to different kinds of data. And really the frontier here for folks like us is when we write grants and we go to cloud brokers and we put in money for cloud services and grants, which is coming, right? There's a point at which you're not going to be able, just like every grant you write in some overhead for the high performance computing system or write in some storage for the cluster or something like that. In 10 years, every grant you're going to have to write in some cloud services. I mean, I firmly believe that that is the way the world is going to be going. And the landscape is going to continue to evolve. Given if we can get procurement more effectively, we're going to be able to have more of a seat at the table in driving forward the way in which the landscape will evolve, and pushing different providers to expand their asset catalogs and to add options to wrangle data within their own ecosystems. And I'll stop and I can give an example for people if they want. Like y'all can couple me with questions, or the folks online can throw virtual rotten tomatoes at me because they know everything already and I've wasted an hour of your life that you won't get back. But there you go. Questions? Yeah, sure.
So as you mentioned, people write in overhead on grants to use high performance computing centers. So I came from Argonne National. Yeah. So does that mean like less money for places like Argonne? So people also apply to go do some of this data intensive work at the supercomputers and soon to be exascale computers. Do you see these services taking away some of that sort of market from the national labs and the computers, or I know CMCC also has supercomputers?
I don't know. I mean, I had talked to people at NCAR about using, what is their thing, a Yellowstone or something like that. And it's just a nightmare to get access. It took me 2 years to try to get access to a big DOE machine at PNNL, and then they shut it down. A month before a month after I finally got access. And so I just think with persistent disk and compute instances that can be spun up, we're seeing, especially with the United States, I don't know about Europe, but with United States computer government systems, and given the reason that large parts of the Earth system grid were offline, not many people know this, but large parts of the Earth system grid were offline in 2015-16, were because people hacked into it and used that system to mine Bitcoin, right? And they had to like shut everything down and basically erase disks just to get them out of there, completely change the access, beef up the security, and then load everything back in. That was a several months long process. I talked to the person at DOE who basically got a promotion from picking that rock up and putting it on his back. He's like, it was a nightmare. Facilities hosting is a nightmare.
Yeah.
And so I think what is going to happen, it's going to move to applications that are basically, government work that's secret, that's stuff that people can't. I mean, Argonne was the nuclear weapons complex. Those supercomputers are bomb computers. They're used to, when you're under a test ban treaty, you have to simulate the physics of the explosion. You can't physically test it. So I think it's going to revert to the use of those assets. I know that US Department of Energy has this huge initiative. They just released it 2 weeks ago, right? On exascale computing and all of this kind of thing. But those folks are building the next generation of and running the next generation of climate models. They're not, small fish like me who just want to use them. So I think we weren't the kind of people who those things were targeted at in the first place. I think a lot of sound and fury and a lot of noise was made about how we would extend those Starship class big computers to normal users like us and diffuse computing capability. But if I look at my own experience, and I have been on US Department of Energy money for 20 years, right? I've written grants to US DOE. And I'm a long-time grant holder. I don't have the security clearance, but they know who I am. the difficulty of getting access to that US government system was just monumental. If I could put my credit card in and put this in here, why bother? And so it doesn't strike me that I was the kind of user that they were after, even though they said they wanted to democratize. There was no real on the ground effort on their part to streamline access for someone like me. So I just think it's more access for us. And, you know, if they end up shedding staff because of it, where do you think those staff are going to work? For higher pay. So I'm really not worried about the government. I'm really not. I'm just not. They pay my salary. I thank them. This work is funded by them, but I'm not worried. They'll figure it out. Other questions?
Yes. Could you give us some examples
Okay.
about the
All right. I'm getting called for an example, so I'm gonna stop my share and then reshare something else. Hang on 1 second. This is what Microsoft Planetary Computer looks like. This is where I've actually done most of my work. Let's try and lead you through something and run quickly. It's a California health application that I'll actually present on, I guess, next Wednesday, right? Yeah. All right. So what we did is what we wanted to do. So I am in the native Python environment in Microsoft Planetary Computer. What we wanted to do was we had all this health data for California. It was confidential health data. My enterprising graduate student, Yasmin Romiti, she went through a year of the institutional review process to get access to confidential health data, individual patient records. And so we have patients' zip code of residence, something about their demographics and their date of admission to hospital in California. And we have the universe of those people from 2012 to 2019. So 53 million individual patient records. What we're trying to do is to correlate people's illness that they showed up at the emergency room for with the temperature that they experienced on the day of and the days prior to their date of admission to understand the burden of climate on mobility. We have been doing that work separately with ERA5 land. ERA5 land we queried through Google Earth Engine. So I did not use Google Colab, I used Google Earth Engine to process and download those data. And we matched them with patient records on our high performance computing cluster. We had to, because per the terms of our data agreement, those data are so sensitive that they can only be accessed on a secure encrypted partition on BU's high performance computing cluster. And if we move the data, we are in violation of the United States Public Health Service regulations. Okay, so horses for courses. These are the constraints that project was under. Something else we could probably move the data up to Google Colab, Google Earth Engine. We can't with those. We must work on our HPC system. And so we need to move processed as much as possible data to that system. And so when we deal with our transfer function that links, it's a nonlinear spline that links temperature on the day of admission to the probability of admission in a GLM model. It's a GLM with spline run through CEST because of the very high number of fixed effects, patient fixed effects. Once we take that spline, we want to use that as a transfer function to understand, well, what the impact of climate change circa mid-century would be. And so we use NASA Next GDP6, but we have to subset to California and process for California. And so the Python packages that we use are Planetary Computer, which gets us access to that system. You must use it every time you work with Planetary Computer. DASC for the scheduling, FS-spec to connect to different assets that basically opens file handles. As well, connecting to the client, to the files, you need something to access stack assets. Stack is spatio-temporal asset catalog. It is the way in which the data are actually held in cloud native format that you are querying. For the numerical processing, the data cube, we use XArray. other functions to get the data out of Xarray. We use NumPy and Pandas, and because we have to subset to different geographic regions, we use GeoPandas. We also want a mask from an external data set that gives us California region, so we use an application, a package called Region Mask. It's new, it's just been updated, but it's not on the system, so we have to install it because it's not there. The catalog we open is Planetary Computer API, Spatiotemporal Asset Catalog. We're getting one of the collections, the feature collections that they have is NationalX GDDP6. And what we want to do is get a list of summaries by model for each of the 35 or so models that they have processed. I'm going to choose, for a very simple example, model number 5. I think that's one of the CMCC models. Thank you very much for your excellent work to help out with this. You did your part. Now I'm trying to do my part, standing on the shoulders of giants. And I'm going to use a 5-year application just so it runs quickly. So my start date for historical is 2015. Actually, the historical period for CMIP6 ends in 2014. But I'm doing, since the period of record is 2012 to 19, I'm going to do 2015 to 2019, and then 2025 to 2055 to 2059 for the mid-century. And I'll do a current climate and mid-century instance for each of the models that I translate for each of the SSPs, because even 2020 is not the historical period, it's still part of each SSP. And so let's go, let me make sure I can restart the kernel, make sure it runs. Is it running? It's taking its time. You see the star. Right, so the model I'm running, I've chosen CMCC CM2SR5. Okay, so now in the next cell, what we're doing is we're going to search the catalog, and every cloud provider does this differently. The search keys that Microsoft sets up in their databases, you set the collection, you set the date time query, which is usually begin year / end year. But in Python, it turns out that if you have range, the beginning is inclusive of the range, but the end is not. Here in their querying of their catalog, the beginning of the range is inclusive and the end of the range is inclusive. It's just one of these sort of pain in the neck things to keep track of. And you can query by model and query by scenario. Why I'm querying by model is that, for instance, not all models have TAS, believe it or not, when they ingested. So if you do a bunch of models at the same time and try to be greedy and work on all of the models and go home or go down the pub and drink beer, it will fail because it will run across a model that doesn't have the asset that you're asking it to get, and it's just going to crash, right? There goes your time. So doing it piece by piece, you know, Giacomo, I lent him some of these data and he's figured out how to do it with loops, but looking through and figuring out which one has what asset, that's part of being the human in the loop. Okay. So just running this, I can create, I can create individual searches. And for those searches, I can get all of the items. Your items are, are basically your climate variables, from those from which I'm going to choose things like Tasman, Tasmax. And then you can't access them unless you use these functions here, which is sign. And that's why you need Planetary Computer. You have to sign these things out, because essentially what happens is that when you search the catalog, what the catalog returns to you is a series of URLs at windows.net. So in theory, you could just connect over the web and download these things from windows.net, but they're encrypted and the server will reject your network connection just trying to download them, because Microsoft, having processed these assets, treats them as proprietary. So you have to sign them out from within the cloud. So here again, victims of capitalism, right? We have to work around the ways in which the providers who host the repositories of these data and give us free access enable us to access them. Here is the magic. So here, Python being a nice language that it is, It's not like R, where you should never use a loop because it's slow. Python was built from the ground up. So if you use lambda or you use map or you use loop, it's the same underlying constructs and pointers. And so there's no speed up associated with doing something one way or the other way. Underneath, it's all vectorized. Good, good. What that allows you to use is a functionality in X array, which I opened as XR, called OpenMF dataset, which is open multi-file dataset. So what that means is that I can open, in the way Python makes nice, an array of things with one function call, but I can dynamically assign the elements of what is being opened in that array by putting my square brackets for the array, and then using FSpec to create a file handle over each of the items for the particular asset I want from that item for the href or URL associated with that asset in Microsoft Planetary Computer's internal spatiotemporal asset catalog system. And I can just do open for each year in the range 0 to 5 years. So efficient slicing and dicing, and then loading everything seamlessly along one long command line into an X-array data set, which I can then do geospatial processing on. And I can do this for a bunch of things simultaneously in the same cell. Also, Malcolm will laugh, climate modelers are a very special breed. So most of us think of latitude and longitude of going from plus 180 to minus 180. Climate modelers, of course, must do 0 to 360. Can't be the same. No. So in order to query with other geospatial assets that go from minus 180 to plus 180 in their coordinate systems, I have to auto-rectify. It turns out that I can auto-rectify easily using Dask in the background so that it will chunk the auto-rectification, doing chunks of cells without me seamlessly working on it. And each of these rasters, by the way, I have not spatially subset. So this is the whole world, right? This is slices of images that give me years, days and years over the whole world. So this is not small, right? I can use Dask to do this efficiently in the cloud. And so I just say with Dask config set, use array slicing, split large chunks. And it seamlessly allocates this over Microsoft servers in a way that does the load balancing and doesn't fail too often. I've had it fail like twice, but I've been doing this several times. I keep the attributes of what it is I'm slicing and dicing and just reassign the coordinates using some enterprising code that Ray Bell put up on the web. Lots of late night searching for how to do this efficiently. I can never take credit for anything. I just find and steal from other people. Running this, right? It will take a couple minutes to run, especially because it has to send the instructions in the cloud, and we're in mid-afternoon in Western Europe, so it's going to be a lot of work on the system. Then what I do while that is executing is I have loaded my own file. Let me show you where the file is. I have loaded my own file in my partition. I have a little code partition here, and I'm using this, which is a downloaded data set of California building climate zones. So it's a GeoJSON, which is, I could have used a shapefile, but I said, let me invest in using GeoJSON because GeoJSON is built into the fabric of Python. Let me ingest those climate zones. And what I'll do is now, having ingested the scale of the human system that I want, I can then, those assets that I've just processed, that just finished processing in the background, I can now subset them down to my region of interest. So I can load the data. And essentially, I'm using that region mask package with its syntax. I won't go into it in the interest of time, to create the mask of all of the CMCC model grid cells. Okay. Still thinking. It's still. Oh, it's run. Okay. And so now I can shrink the data sets by clipping them to the California bounding box, which I can find from my total bounds attribute on my GeoJSON that I've read in. And having subset them, I can create my mask. And then in the next, I can just plot what does my mask look like. Right? So those are my 16 climate zones in California. You see 14 and 15 is the southeastern desert. 1 and 2 are the northeast coast. 4 and 5, 3, 4, 5 are the central coast. 8, 9, 10 are the south coast and LA. 11, 12, and 13 is the Central Valley. Okay. We can then show how to subset, and I just picked the 950th image in my image collection, and I subset that to where all of my mask is less than 16, because 16 gives my IDs of my polygons. So I'm essentially doing by hand what Google Earth Engine is doing automated in the cloud that I would instruct it to. And this should give me a nice matplotlib plot. It's thinking. And this takes time. Just plotting one slice takes time, because now you essentially tell the cloud to compute and return the data, right? And so everything else can be arithmetic that's just done in pointers. But now you say execute, now you're actually running a program and physically moving the data over networks. And this is what our data look like. Each of those grid cells in the back is going to be assigned an attribute, which is going to be the number on my mask. And so now I can do what I really wanted to do, what I came to do, which is apply by zone, right? Grouping by day of year, and extracting using the xarray2 data frame call, extracting all of those pixels over all time slices to a pandas data frame, dropping the white parts in the ocean and in Nevada and Utah, dropping the parts that are NAs, and then finally at the end, concatenating all of the resulting pandas data frames together to give me one data set and adding a column that tells me which GCM it is I'm talking about, ready to take all of this system and wrap it in a nice loop. All right, so let's run. It's going to take a while. Last time I did this, it took 3 minutes and 19 seconds, right? So if you think about it, the work to set this up, to query the catalog, it would take about a minute and a half, 3 minutes, 19 seconds of work to run, then another maybe 2 minutes to actually export the pandas data frame as its CSV. You're done in 7 minutes, 37 models or 35 models by 7 minutes, you're home in time for dinner. Pretty remarkable. Pretty damn remarkable. Okay, it's still running, it will give me a time, but I'll go on the next, in the interest of time. The last thing is to save with my path and use the pandas df to CSV with the path and no index, you know, row dot names equal false, right? And in write.csv. That's the equivalent in Python, and that's it. It will finish executing in a while. So questions, other questions on this?
What is panda?
Pandas, pandas is like data.table.
Okay, yeah, so it's like a function in Python.
It's a package in Python that gives you all sorts of functions. Malcolm, go for it.
Can you hear me?
Yeah, loud and clear.
Thank you. Very interesting talk, Cian. As always, lots to learn. I was just curious to ask this question. As we move from local computations and running the regression models onto cloud, what is your take on making these codes replicable from the publication's point of view? How difficult do you think this is going to be to make all this workflow publicly available to the journals and to the users to replicate this?
I think it's going to dramatically simplify, because all you have on your GitHub is basically just the Jupyter Python notebooks, right? Create an account on this system, run this notebook, you get figures X, Y, and Z of the paper. That's it, because you never touch the data. That's the beauty of it. I'm literally not touching the data. So the frontier that I am looking for is if Laurent Berger ports CEST to Python. The moment that happens, I'm done with R. I'm done. I'm done with it. I mean, it's like, what point then would there be to move these processed data out from Microsoft Planetary Computer? I would just be moving into a high performance system to log into the same environment, to run a package that I could install here, to run a regression that I could do without moving the data. That's the point. Here we go. 2 minutes, 14 seconds. Actually, that's the desk in the background. Sorry. Wall time, 3 minutes, 39 seconds. It's busy in Western Europe this afternoon. Lots of big corporations using the cloud. This is what we look like. We've got day of year, latitude, longitude, TASMAX. Notice how it has kept from the mask my zone identifier that I wanted. I added a column for each SSP, given which SSP iteration I processed, and the epoch, either 2015 to 2020, it should be 2019, sorry, or 2055 to 2019, and the GCM. So here is my file. I go back to my file system, CA health, and this would be last modified. Oh, I have modified it. Sorry, I have one last thing to do. Run that, and you should see the code up here.
Just one quick question.
Yes.
I mean, okay, here and
Can you yell for the
no, just about the uploading our own data that we might need, our own shapefile. Of course, here it's fine, or Google Colab as well, and in Google Earth Engine, it's also fine to upload things easily. There's no.
Click. It's fine. It's just if I would open up the shapefile, I wouldn't just download the shapefile and then re-upload. I would open the shapefile in R and just check it out. You know, I've opened shapefiles and simple features, and there's some nonsense going on inside. Just check that it works for you with a calculation, and then upload, and then it'll be seamless. It's pretty easy. And here it has shown up a minute ago. TASMAX, CMCC CM2 SR5. Right? There we go. And I can just right-click and download it and put it on my high-performance computing system. And again, I'm only doing that because I have to use it there. Right? The next phase of this is not downloading at all. It's when I do the estimation, extracting the splines from that system, and then putting the splines as the next cell down. Right? So that I don't, instead of moving the data, I move the instruction. It's far easier to upload. Here's the knots in the spline, and here's the equation of the cubic that captures them and connect it to these data than it is to move the data. Okay, thanks everyone.
Yeah, so this was really just an introduction. Ian is going to be here for a week, and he is going to be here to talk with you. So just take advantage of this opportunity. And yeah, I also wanted to remind you that there are actually a few appointments in June. So next week on Wednesday, Ian is going to give a talk on health and climate change in San Giobbe, the Department of Economics, 12:15. Then on Friday, we also have another workshop this period, this month of June, we're also hosting Jennifer Dunn. She's a professor from Northwestern University in chemical and biological engineering. She's also the director of a center on sustainability and resilience. And she will be visiting us for the month of June. So it's also a great opportunity to host you here. Thank you for coming. And yes, this is all for, I would say, for now. And then more announcement about events and seminars will come next week. Okay, thank you. And
thank you all.